common misconception in physiology is that homeostasis is somehow related to an equilibrium state. So let's first talk about what an equilibrium state is. You recall from basic chemistry that if you have a reversible chemical reaction that's in an equilibrium state, then the rate of the forward reaction equals the rate of the reverse reaction or backward reaction. In this equilibrium state, there's no change in the ratio of the products to the reactants, and the concentrations are stable. So that superficially may look a little bit like homeostasis and the fact that you have stability, but let's take the example of glucose in a human's blood. That's relatively stable, despite the fact when you take in a meal, you'd expect glucose to go up rapidly, and then between meals it should decrease. In fact, it does do that, but despite those, the influx of glucose from a meal and then the time, essentially the fasting times in between meals, you actually maintain a fairly stable level of glucose in a healthy individual. Now, it turns out this has nothing to do with a chemical equilibrium. The concentration of glucose in the blood is relatively steady because there are homeostatic mechanisms in the body that work to constantly maintain the blood concentration within a limited range of values. So, for example, if you have a drop in blood glucose concentration that occurs as glucose is taken up by cells, say you're between meals, so your cells are using up glucose for energy, well, your liver will release glucose into the bloodstream, and that helps to make up for this, and that helps to maintain a relatively constant glucose level, even in between meals. Thus, the concentration of glucose in the blood is in what's called a steady state. So it's not an equilibrium, it's a steady state. And this, in the short term, this steady state is maintained by essentially constantly moving glucose between different compartments that we've talked about, the intracellular and extracellular fluid compartments. So, for example, if glucose, as I mentioned, if glucose levels are too low, then glucose can be released by certain cells into the blood. The blood is a part of the extracellular fluid compartment, and so that helps to maintain blood glucose levels. Now, in the long term, of course, your body would become depleted of glucose. You're constantly using up glucose in most of your cells. The glucose steady state is maintained due to a continual influx of glucose and or materials that become transformed into glucose. So essentially, you have intake of food, and this helps to maintain your glucose levels. So again, this is very different from a chemical equilibrium. Chemical equilibriums do not require constant influx of materials. Now we can look at this in another way. This is a picture from your graph from your textbook. In a state of chemical equilibrium, the chemical composition of the body compartments should be identical. But what we find is if we look at the composition of ECF and ICF, we find that the concentration of many substances are different in the two compartments. So, for example, sodium and chloride are far more concentrated in the ECF than in the ICF. And potassium is more concentrated in the ICF than the ECF. So, as you'll see, the body expends a considerable amount of energy to maintain these ions in a state of disequilibrium.